You can see it. Hello? Check. Let me check the sound. Hello? Can you hear me? Is it clear? Oh, okay. Yeah.
I should put my notes too and laugh like I'm serious.
Yeah. We post on YouTube that. Yeah. Start. And two.
Can we post this one on Discord as well? Okay, yeah, check this one. Just write my observations.
So, hi guys. Welcome to another session of zkSaturday.
Great to be here.
So we'll be discussing Verkle Trees today. So the point of like discussing Verkle Trees is like for state proofs and like interoperability in blockchains. So like one of the major issues with interoperability is the cost of verifying the states that you are trying to pass across these different chains. Like the usual is the Merkle Patricia trie, and it has a very large space complexity. Like the space complexity is, I think it's O of k log. Is it verify that? It's O of k log n. Yeah.
What is K?
K is the arity. Well, K is the arity of the tree, like the arity of the Merkle of the Patricia trie. So now for a Merkle Patricia trie, the number of like buckets it holds, the number of buckets it holds. Yeah. So it has like the usual is to have a 16-bit Patricia trie, like 16 base 16 Patricia trie. Yeah. So in the base 16 MPT, so you have like the root node. So the root has like 16 branches. It can have a maximum of 16 branches. So that's the K. So we have this is then up to 16. So that's 0 to Z, F. Yeah. So it has 16 branches max. And now, because it uses like cryptographic hashes to like take the commitments to each of these branches. So each branch will also can have 16 children too. This one also can have 16. The same goes for this. And every branch in between. So let's say you want to calculate the roots commitment. You have to like hash all these branches, feed it as the value for this. Like the hash of this will be the value for this. Then the hash of all this will be the value for this.
So it's recursively hashed
Yeah.
to the top.
So you recursively hash it to the top to generate the root hash.
Where is the data stored?
Yeah, like each branch can have a value. So the value will be the hash of its children. The value for each branch will be the hash of its child branches.
What
Yeah.
of the value of the node that you're trying to store inside the tree?
The node you're trying to store inside the tree.
Like, is it only on the leaves or is it
Yeah,
around the tree?
I know, like the nodes are just like the branches. You trace the tree to its leaves. So the leaves are where the actual values are. For each node is like the encoding of the node, yeah. So you just have the hash.
What the person says like a node is an enum.
Yeah, exactly. So you can have like the node can be this, can be an enum. So it can either be a hash, like this, yeah, or a value. Yeah. Yeah. Or like you can even have like, let's make it better. You can have a leaf node, then a branch node. Yeah, basically. Or you can have other extension, like, yeah. Ethereum has extension nodes, but you can basically have a branch and a leaf node. So the leaf nodes are the ones at the bottom where the actual values you inserted in your tree will be. But the branches are like the commitments to these leaves. Yeah, right. So you hash everything to get to the root. So let's say we have a leaf at this branch. Let's draw a cleaner tree. So, just yeah. So let's say this branch has a prefix of 0, like
Prefix or index.
yeah, index of 0. Yeah, index of 0. 1, 2. So now let's say we have another branch at this index. So we have another branch. This also be like index 0, 1, 2. So let's now say we have a leaf here. This is a leaf. And it has a value of, let's say, yeah. So now, to get the proof for this leaf, let's fill some other branches here. So if this branch is empty, this part is empty, we have this empty. Let's say we have another leaf here. Let's say we have another leaf here also. All these are empty. Oh, yeah. All these are empty. So now, let's say we want to get the proof for this leaf, for this particular leaf. Because like we're using hashes, cryptographic hashes, we need to provide the sibling nodes to be able to hash it up to the root. So we need to get the proof for we need the hash of this leaf. To get the proof for leaf A, that's it. We need the hash of leaf B. See? Then, after that, we also need the hash of this leaf C. Since every other point here is empty, we just need the hash of this.
Are we getting the hash of that because we want to know what is in this plot table?
Yeah, we want to know what will be the value of this.
If it had 2 keys.
Yeah, you also get the, yeah. Yeah, we need the hash of this because that's the only leaf that's currently here. If there were 2 leaves inside this place, we just run the hash of the value that's here. Yes, so we need the hash of this, since every other thing is empty. So we can now recreate the root hash from there. We get the hash of this. We know this leaf. This is the leaf we're trying to prove its existence inside this tree. So the verifier is going to hash this one combine it with the hash of this, hash both, and that will be the value for this. Then it will hash this also, then hash the entire branch to get the root hash. Yeah. So if the root hash checks, then the membership proof also checks. Yeah. Okay, so now you can see the issue with this MPT is that because we always need to provide the sibling nodes, the hash of every sibling node on the path to the roots. So like if the tree gets larger, the proof size will also be increasing because you'll be like for every branch, you have to provide the hash of that branch. Every branch on the let's say this is the key path we're trying to prove now, from the roots to this index to this index here, then to the leaf. Imagine we had a value here. If we had a value here, we'll have to get the hashes. We have to provide all the hashes of all these nodes to generate the proof. So that is not really it's a scalable way to grow states proof messaging, scale state proof messaging across multiple chains. So you need a cheaper means to verify membership proofs for values inside the tree, because in Ethereum and all these other chains, we are paying for the core data. You actually pay for the data you are submitting a transaction, and you also pay for the execution of those algorithms for verifying those proofs. So because of the size of this Verkle Patricia trie, it's not very efficient for state proof messaging. We can get better value by using a scheme that will provide us with very constant size proofs, or very small proofs that don't grow with the size of the tree like that. So. Okay. So now that's where Verkle Trees come in. So Verkle Trees, they are similar to the Verkle Patricia trie, but now instead of using hashes, we'll be using polynomial vector commitments, and you can use polynomial commitments as a vector commitment also. So that's why it has the name Verkle. So the V stands for vector commitments. I think it should be vector commitment Verkle tree. Yeah. So, yeah, vector Verkle tree is better. So now, Verkle trees is just replacing, instead of using a hash, you just replace where you're hashing. Instead of using a hash to calculate the commitment for a branch, you just use a vector commitment to commit to the entire values on that branch. So that will give you a constant value. So let's convert that tree we designed the first time into a Verkle trie. Yeah. So we have a root now. I think I have one as well designed here. Okay. So we have this. And you would notice something because of how Verkle Patricia tries work. You can see that the size of the number of indexes in each branch is you have to use a small index. That's why we use 16. That's the reasonable branch length to use without incurring the extremely large proof sizes. So let's say we have this. So let's say we have this tree now. So in this case, this tree is going to be like a 256. It have 256 branches. So that means the K in this tree will be like 256. So because the K is 256 now, I'm using like the index of each node is like just a byte. Yeah.
Sorry,
With 32 byte keys rather.
can you give us the math for this? Like, why is it magically bytes?
A byte, okay. So now we have K equals 256. And we want like each branch to have 256 children, basically, like the root from the root to have 256. But now we also need to be able to like index that each node easily. So now you can see that in the base 16 tree, the indexes are just the letters of base 16, 0 to F. But now in like a 256, when you have 256 children, how do you index it? Like you know that a byte, the maximum value inside a byte, a U8, is it 255. So it starts from 0 to 255. So if you have this, like this just gives us an easy way to like index the entire children. So if you represent each index with a byte, you can have from 0, 1, 2, 3, 4, 5, 6 to 255. So that's, if you count it, that's 256 like children. So that's why we use a byte to index each of the children. Yeah.
Sorry, I have a question about still this bytes representation.
Mhm.
What happens if we use a bigger byte?
A bigger byte.
Yeah, bigger byte size. Like, is there any cost to this?
If you use like a bigger byte size, in what sense?
So take for instance, we wanted a larger tree size.
Yeah. Like
Say
1024.
1000.
Yeah. Okay. Yeah.
We need something that we can fit 1024 inside, right? But there is no standard
Yeah. There's no standards.
number system for this.
Yeah.
So we, of course, now have something bigger. That's like a U16,
Yeah. Yeah. What's this?
which represents with 4 bytes.
Mhm.
So, is there any penalties for that?
Using a larger
A larger byte?
larger prefix.
Yeah.
And I think like if you're using a larger, like you have to your keys now, you have to use larger size keys too. Yeah.
So is there a problem when you use larger size keys? Like what's the cost? Does it affect the cost of the proof or something?
I don't think it will affect the cost of the proof. Like for Verkle Trees, I don't think it will affect the cost of the proof per se.
Okay, that's good.
It's not affect the cost of the proof. It's just like the overhead of encode or finding a new number system to like match. Because now you need to create your own scheme to index each node in each.
I mean, you just use the first 2 bytes.
Yeah, but you know 1024, like U16, the max, the like is a large number.
2 to the 16 minus
Yeah, 2 is 16 minus 1.
Yeah, it's 4 bytes.
Yeah. Yeah, so
How the commitment cost since it's now
yeah, it doesn't change the commitment.
Oh, really?
Like the commitment cost or like
cost to vector commit to this.
yeah, it will be more expensive to prove it. Yeah, it will be more expensive to prove it
Okay.
because you have more items to now like commit to. Yeah.
So it's computationally more expensive.
Yeah, but not. Yeah, the space. Yeah, not like we're not really changing.
Depending on the commitment.
Yeah, depending on the commitment scheme. So it will be computationally more expensive to use a larger tree, but it will still offer you better advantages over the Merkle-Patricia try if you have a good machine to run your computation on. So now. Yeah. So now the prefix for this node is this. So that's this 1 byte. Yeah. So let's see. Then so let's say this node just has 2 leaves as its children. Let's see. So let's say this node also has another node as a child. So now, we have a root node. So this is like we're using k equals to 56. So the index for each node is like 1 byte, a single byte. So in this node, let's say the index for this particular node is this. That means this node occupies the index like 0f0 from the root node. So this 0ce from the root node. So this is a node. It has 2 leaves. This node has another node as a child. You can see that this node has 2 leaves as its children. So that means that's why we have a node here. Because if it was just a leaf that was present at this index, we would just put the leaf there. But now that there are 2 leaves that divert from this particular prefix, we need to have a node then represent the leaves underneath it. So now, from the Verkle, so now if it was a Merkle Patricia trie now, you know, like we'll have to hash this to put it as the value for this node. Hash this, then hash the value this node, put it as value for this, hash this with the hash of all these recursively to get the root node. But now, in the Verkle tree now, since we'll be using like a commitment scheme, so now what do we have to do? We have, obviously, we'll still have the hashes for our leaves will still be hashed. We still have to hash our leaves. So we'll hash these 2 leaves. But now, instead of now hashing them, hashing the 2 leaves to create the value for this node, we will now make a commitment to the hashes of these leaves. So we'll say, if we're using the KZG commitment now, let's say our commitment function is let's say I don't know, CF or something. Or let's just say C. So we'll take the commitment to, so we have hash, let's see if it C. Leaf E. So now if we want to compute the root commitment now, we have the hash of leaf. Let's say, I'll just label the hashes with H. So let's say H1, this H2, this H3, H4. But let me just use letters. Hash of A. Then hash of D. So we have all these hashes now. So now we need to commit to these hashes. But to commit to these hashes, we need to be able to transform them into like a form, like a list of items that we can commit to using a polynomial commitment scheme. So we have to first have like a function of some kind that can map these hashes to a finite field, to values inside a finite field, so that we can commit to them. So we have, let's say we have a map function that takes a hash and returns like, let's say, each like a member of finite field. Yeah. So we have a function that does this. So we'll convert all these hashes into their finite field form. Then we now we first have to interpolate to get the polynomial for, okay.
Why do we have to map it to a finite field specifically?
Yeah, because we have to deal, we can like use raw numbers, like regular real numbers, to do polynomial commitments, because like real numbers, they are not cyclic or something. They can keep going. Like the computation is not, you can't contain the entire values of real numbers. Like when you're in a finite field, because it's mod something.
No, but why are we in a finite field?
Discrete log is hard.
Yeah, okay. This feels like it's hard in a finite field.
For KCP specifically. The discrete log will be hard in a finite field.
Yeah.
And that's important for security of KCP.
So we have these values. So we map them to values in a finite field. Then we now have to, before we can commit to, we commit to polynomials since we're using a polynomial commitment scheme. So we need to first get the polynomial we're committing to. So the only way to get polynomial is to interpolate. So we have an interpolation function that would take, like now, when we map these values, we'll have a set of values. Let's say we have H1, H2, like HA, B, HC, HD. Yeah, that's all. So we have these values. So they will be in pairs now. We want to interpolate in such a way that we have, let's say, I interpolates these values. Let's say H of A, comma, H of A. Let's see. Yeah. So we want to create a polynomial such that we have, let's say, phi of one of these values, like the values inside here, will give us the actual hash in some finite field here, arithmetic. So we want like a value, like we have these hashes. We want to be able to, we want to interpolate a polynomial that when you add the value that you have mapped that hash to, when you put that value inside as the value for this polynomial, as the x coordinate, it will give you the hash that you initially put, that you mapped to.
So you're mapping the real number field to
This one, it will still be in like a finite field. Yeah.
okay.
Yeah.
So when you do the evaluation of the polynomial, what are you obtaining?
We'll still obtain it like a value in the finite field
So what are you evaluating
on
on?
the polynomial.
What's the input into the file?
Yeah, you know, like for all these hashes, we created some other values that we map to those values.
Yeah.
So like we have a function that creates a set of values that are unique to each of the hashes. So that's basically what we do. you know, like eventually these hashes, they are still numbers.
Yeah.
So you can also just get their representation in a finite field. But this map function is to generate some set of unique values that will be like this. You want this, basically you want these hash values to be the y, to be the like solution, and the values derived from this map to be the x coordinates for the polynomial. Yeah. So once we have this, once we have a polynomial that does this, once we can interpolate to get our polynomial, then we can now commit to that polynomial and add it as the value for each node. So for each node now, we'll have to run that same thing. We'll get a set of values that are unique to each of those hashes. Through this our map function, then we interpolate to get the polynomial that represents those values for this particular node. Then we find the commitment for that. Yeah. Yeah.
Set of numbers are the 256 individual items in a node.
Yeah. Like it depends on the node. Like a node can have the full children filled up. So we'll like run our map function for all the like nodes to get those like the x values that we want to interpolate over. Then once we have the x values, we have the hashes which we want to be the solution to that polynomial at each of those points. So okay, let's say we have we want x and y values. So now the x values will be some unique values that that based on our function represents each of these leaves or each of these hashes. So let's say we have xi to x, let's say n plus 1. Then we now want, when you pass this value, this x value as when you pass it as the option to the polynomial, we want it to give us, let's say we have xa here. Like let's say xa represents the unique value for this hash. You want a polynomial that when you pass this value as this xa as a value for x, it will evaluate to ha. Then the same thing, you want b. Yeah, you want this. So that's what the interpolation does. So like, interpolation is like a way to just guess the polynomial from its evaluations. So you now have, basically we have, from this table we'll have like xa, comma, ha, xb, comma, hb, xc, comma, hc. So we have all these values now to add like as many as possible. Then when you run an interpolation function over this, it can help us generate like an approximate polynomial that represents this data that we have. So anytime you now insert any of these values into the polynomial and evaluate it, you will get this other value. You get this other value.
So what is XA now? Like in the Verkle tree.
Okay, let's.
Is it the prefix or the?
No, it's not a prefix. Like basically each leaf,
Value.
to get the hash for each leaf, you hash the key and the value, everything.
Okay.
To get like, this would be hash of full key, comma, value. You hash the full key and the value inside here to get the value, the hash for this leaf.
That's hash, right?
Yeah. So now we want to be able to get a polynomial that represents the values of all the hashes in this branch.
But what are we going to put inside the polynomial? Like, what's
Yeah.
that X?
So like that's what I said, we can have a function that does that, like a function that will generate, like anytime you pass in a value, it will generate a unique, like an index, a unique value inside a finite field that represents that you want to use as the x value for that particular evaluation.
But does that mean that the ordering of the nodes,
It's random.
it doesn't matter? Does that what you mean?
I thought it depends on the key.
Yeah, the origin of the nodes.
Yeah.
Yeah, the origin of the nodes depends on the key, like by default.
Yeah, but the
feel from.
So like I can flip leaf A and leaf B now.
Mhm.
The function will still be the same. I don't know if that makes sense.
Like flip the
Like
value
if I
here.
put A, like
Mhm.
to the right.
This one.
Yes.
Mhm.
So you know there's leaf A and then there's leaf B. The child.
Yeah, yeah, yeah.
Yes.
But they have different indexes.
They have different indexes. But I could potentially move leaf B to leaf A and move leaf A to leaf B, and I'll get the same polynomial
Hmm.
after interpolating.
After interpolating.
Yeah. But if I was using the
Yeah, yeah. Are you going to get?
the key to the interpolation, then it should apply. But I don't know.
Yeah, I think your function that should generate those unique indices should take into account all that, like so that the leaves cannot be switched. To, yeah, it's not just be like a regular function, like, or generally in this kind of case, we just use like the roots of unity as those values. Yeah, as the interpolating set. Since our k is cos like 256 is the power of 2. So we can use the roots of unity as, like we can say, let's say we have omega as the root of unity for this k equals 256. So we can say that for each node now, when we're interpolating the polynomial for each node, the x value for each index will just be omega raised to the power of that index. Omega I, yeah, to omega k, yeah. Okay, k minus 1, yeah. So if we have, like, if we're using the roots of unity as like the x values for our interpolation, so we just have these constant values we use, then we have the hashes, yeah. Then we interpolate to get the polynomial, get it out. So that way, if they can switch the position of the leaves to get the same polynomial anymore. Yeah. And I think using the roots of unity will make the evaluation easier in some cases when we're doing like the DFT and inverse Fourier transform and the Fourier transforms. So now, let's say we have, okay, let's even just say we're using the roots of unity now. So for each node now, we use the root of unity to a power of the root of unity as the x value for that particular leaf. Then we want a polynomial that, for each node, we want a polynomial f of omega I that will give you, let's say, the hash of the leaf. Yeah. Obviously, the hash of the leaf will represent it as a value in finite field. Yeah. So this will be our polynomial. This way, once we have this, we can now commit to this polynomial using any of the polynomial commitment schemes. So we can use kzg to commit to the polynomial. So once we commit, we have the commitment to this node, let's say C naught. We have then like now, we have C naught here. Let's say we have this C, let's say C2. So now if we want to get the commitment to this node too, we also have to do the same thing. Now, we have the commitment here. We'll hash that commitment. That will be the value of this node. So then we run that interpolation again to get the polynomial for this particular set of values in this node. Like the hash of this leaf will be one of the values. The hash of this node will be one of the values. We run it again to get the polynomial for this particular node. Then that's C1. So now we have these two nodes. We have C1, C2. To get the commitment for the root node, we'll also do the same thing. So now the value for this particular index in the root node will be the hash of this commitment. And this index also, it will be the hash of this. So we'll interpolate again using these values to get a polynomial that represents the root node, and we commit to that polynomial. So we have the root commitment, CR. So now, if we want to generate a proof, like if we have all these commitments for all these nodes, I want to generate a proof for, let's say for this leaf. We want to generate a proof for this leaf. So now, we have to prove that, we have to provide like an opening proof to this commitment to this node, that this leaf exists in that commitment. That this leaf is part of the values that were committed to by the polynomial in this node. So let's say for leaf E now. Yeah. If we want to generate the proof for leaf E, we need a proof for the presence of this leaf inside this commitment node C. So we have, let's say that was pi 1. C naught. So now, we also need, we have to like generate proofs to reach the root node. Now we need to prove that everything in this path is present inside the root node. So now we also need the proof for the existence of this particular commitment, which is the value of this node C inside this C1. So that would be like another proof. And let's say just a C naught in C1. Then now we need to prove that this node B is inside the commitment to the root node. Commitment to the root node. So now we have 3 proofs. But like in the KZG, in like the let's say in the KZG commitment scheme, each proof is just a single field element. So it's not large. Yeah, group element rather. A group element of an elliptic curve. So this is just a group element, group element, group element. And also the commitments too are also group elements. But like from the Merkle-Patria trie, we will need to provide the hash of this. Then we will need to provide the hash of this. Then all the hashes in between. We also need to provide the hash of this. But now, from this Verkle tree, we can see that we only provide this. We provide obviously the leaf that you want to like prove. We need this commitment, and the root commitment. Then also the proofs. So now, if we are doing like a multi-proof, you can see that if we want to prove the existence of this leaf also, we need to provide another proof. We need to provide a proof that shows the existence of these 2 leaves inside this, then this, then that too. But in this, you can, like the KZG scheme has a way to do multi-proofs, like for a single polynomial. And I think for multiple polynomials, but yeah, it can also do for multiple polynomials. They have a scheme too. But basically, this naive way of generating the proofs, it doesn't give us most of the benefits we wanted from using a Verkle tree, which is like smaller sized proofs. Like we're still providing 3 field elements for the group elements rather for the proof of this leaf. So is there a way like we could just provide just one group element for all these proofs? That's what we want to like look into next. But by default, we'll always need to provide the commitment. Like there's no way to provide the proof without the commitment. Because like in state proof messaging, the root commitment is going to be gotten from the consensus proof for that chain, basically. So that the verifier on the other chain, it only knows this root commitment. So it doesn't have an idea what all these other commitments are. So basically, you need to provide all the commitments on the path to the roots. But we can provide those, but we want to like reduce the cost of generating proofs for each step by combining all those proofs into just one single proof. So, so that's where we'll now look at like the batch proof scheme for Verkle trees. Does anybody have any question? Okay, yeah. So now,
Oh, yes, I do.
okay, yeah.
Updating.
Updating.
Yes.
Yeah, when you update, you need to recompute the commitment. Like if, let's say, we put another value
Yes.
here, or let's say we put another leaf here.
So I need to reinterpolate.
Yeah.
Can I just add it somehow?
No, you can. I think you can add polynomials together. You can add commitments together.
Yes.
Yeah. So there should be a way to. I think there's a way to like add without completely reinterpolating from scratch again. You can just add this new value. Like there should be a delta to the polynomials you can add to get a new commitment. But if that's not possible, then you just have to interpolate that particular node again.
Then you go up.
Then you go up. Yeah. But you don't need to do the rest since you already have them. But every node you add a new value to, you need to get a new commitment for that node. Yeah, for its parent and up to the top of the tree. So the same thing, if you delete the value too, you must do the same thing. Yeah.
Not the Verkle tree. You can use it to store the value of an account.
And you can also use this one to store the value. You can store any value inside this tree too. It's still a tree. It's just the like how you like verify what is inside that is different.
No, I just want to get how, let's say, given an account.
Yeah.
You,
Okay, let's say we have an account now. Let me get the key. Okay, let's say we have an account that has a key. Yes, but usually we'll use like 32-byte keys. But let's say we have this key now, and there is an account. It points to a user account that has just balance and like nonce. So you start you split this key into its bytes. Then you like trace it through the tree. Like you traverse the tree from the initial first byte. So from here, we have AF. So we'll go to index AF on the root. Okay. Well, let me draw it separately. Yeah. So we'll go to index AF on the root. If that index is empty, if there's nothing there, then we just put a leaf node at that particular point. But let's say we put a leaf node that has the full key and the account balance. That will be the leaf. But let's say that place, there is a node there now. If there was a node at this point already, if there was a node here, then let's say that node already has a particular leaf in one index. Let's say 0, F, I don't know. Yeah. Let's say EF. That node already has a leaf here. So now we'll pick this BC index of this node. So we now have another path here. Then we can insert the leaf. That will be the account balance of this user. So the prefix will be, let's say the prefix for this leaf will be 0xAF. And we'll have the full key. That's this full value. Put the full key, then put the value. Value be balance and nonce. But now, if there was already a node at this point too, so we'll do the same thing again. We'll check the index of that node that doesn't have any value, then insert the other parts of the key. Like we'll do that until we get to the end of the key.
okay. When they are going to like know if this entry is a leaf or a node, it has saved
Yeah, like when you are traversing your tree, you fetch that node. So you must, in your algorithm, you must have represented a node, like what a node is, like an enum. So it will be like leaf node or branch. So if you fetch a branch, you know that it has children. Then you look for the next, you advance your key to the next byte. Then look for that index in that branch and try to fill it up. You fetch that index. If that index is also a branch, you advance your key, fetch, fill it. Yes, so that's how you do it. Then once you have inserted this value, you now take your commitments again back up to the root commitment. Yeah. So you can represent the same things you can represent in the Verkle Trees are the exact same things you can put inside the Verkle tree. You're just committing instead of hashing all the children. So now, like before we go to the batch proofs, let's look at. So now, like in the KZG scheme now, like the commitment scheme we want to discuss for the batch proofs, it works for polynomial commitment schemes generally, not only KZG. Anyone that is additively homomorphic, like where you can add the commitments together. Yeah, so like, for KZG, if we have a polynomial, x, z from 2 minus 1, x raised to power. So let's say we have a polynomial like this now. Like if we want to commit to this polynomial, we'll have like a secret key, but we don't know the secret key initially. Like you use the secret key to generate a reference string, and yeah. So from the secret key, we have like this reference string, which is 0 to like the largest size of the polynomial you need. So let's say k minus 1. So the secret key must be as large as the reference string or secret reference string. Yes. It must be as large as the polynomial you're trying to commit to. If not, it's not be sufficient. So we have these values. So now to commit to a polynomial, the commitment is basically just evaluating this polynomial at the secret key. Yeah. But like the polynomial, we already have all these, we have our reference string that is just powers from 0 to the largest degree of the polynomial. So now we can just say I and c raised to power I, L minus 1, or k minus 1. So we can commit to the polynomial without knowing what this secret key is by just using our reference string. We commit to the polynomial. So if we want to prove, like now, when you evaluate a polynomial, let's say we evaluate at, let's say z. We evaluate polynomial at z. So we have equals to, let's say, a value y. So if we have this evaluation of a polynomial, that we can create a new polynomial like that. Phi let's say x minus y. Let me see q. Yeah, I can create this new polynomial. Just this. But that if I divide this polynomial by this x minus z, it will divide it successfully. So I can have this. Like this will give me another polynomial to this quotient. Like the initial polynomial minus this evaluation divided by x minus the evaluation. It will give me another polynomial. that's like this x minus z divides this new polynomial completely. You know, like this value is a constant. This y value will be a constant. So this divides it completely. So from this now, if we have this quotient, we can also now commit to this quotient. Like this new, if we commit to this new polynomial, that will be like the proof in, that's what like KZG uses to represent the proof to this, for this evaluation. So the proof for the evaluation of z of, okay, it will be just the commitment to this. Yeah. And you know, because this is a polynomial, we can also still evaluate it using this, like this entire thing is a polynomial. So we can still evaluate it using this reference string, because we know that the degree of this polynomial will be less than the original polynomial. It will be less than phi of x, like the degree of q of x is less than just by 1. It will be less than the degree of this by 1, because this is just one factor of this, of like this polynomial. Yeah. If you divide, like, you know, remember if you have a polynomial, you divide it by one of these factors, you get a polynomial that's as reduced by one degree, because you have removed one of the roots. So this will be like the proof for a polynomial evaluation. So that's how we got all those proofs for this leaf inside the tree. That's how we would derive the proofs generally. But now, if we want to derive a proof for the entire thing with just one group element. So now, in the case of like multiple evaluations, when you evaluate, you want to evaluate these different polynomials at these different points. You know, like there's a polynomial that represents, it's a unique polynomial that represents each branch. So now you want to get a single proof that works for everything. Yeah, I can just claim this. So we want to get a proof that can be used to represent the opening of all these commitments at those different values. So let's say we have the polynomials for all these nodes as phi of 1. Let's say we have one polynomial, phi of x, 0 of x, phi 1 of x. Yeah. You know, like, because I can add polynomials together, that means I can also add the quotient for the evaluation of these polynomials at different points. I can add it together and to still give me a polynomial. Yeah. So let's say I have, how do I represent these polynomials? Okay, let's use this now. We have a polynomial for this. Let's call this one b of x. For this, yeah, and let's say we want proofs for all these leaves, like this. We want to generate a proof for all those leaves. So now we know we have phi, like what's A? Yeah. Want generate a proof for, like, let's say, let's label the indices for this. Yeah. Let's say this is 0, 1. Yeah. Leave And you know what? We said we're using the roots of unity for everything. So we have, let's say, for this index, that's raised power 1, obviously. We want it to be equal to this HA. We want to be equal to this hash. Then we have another evaluation of this same polynomial. If this lives at index 2, want to be equal to. Then we'll have another evaluation. We have this again. Phi C. For, yeah. This one is 9E. Yeah. So we have all those that we want to evaluate. Then, you know, like, because we are trying to get a proof for the existence of everything inside the root hash, we also need the proof for this, for the commitment to this node but inside this place. Yeah. So for this one now, because we want to generate proof for this, and this. We want to generate proof for this. So we also need the evaluation of this commitment inside this polynomial for this node B. Yeah. And this at index. C1. Which one? Oh. Yeah, I see. No.
C0 is in C1, right?
Yeah, I want proof C0 is in C1. So this.
We need to prove that.
Oh, yeah.
Yeah.
C0 in C1. Yeah, I want proof that this is inside here.
Yeah.
So it should be this B, at first C0, yeah. Then,
Isn't a commitment like two field elements,
yeah.
X, Y,
Mm-hmm.
in the elliptic curve group?
Yeah, it is.
So that wouldn't fit the finite field.
The commitment, we'll hash the commitment, obviously. It will be the hash of C0. Yeah. So the hash is going to give us a single value. Then we have, for the, let's say, we have this roots commitment. The hash of C1 inside the root. Then we also need the evaluations for this inside this.
We have done that. It's first one today.
Okay, yeah, sure.
But you need to do for C2 and CR.
Yes, yeah. So we're hashing all the commitments before we use them as there. So now we have all these evaluations now. I want to prove them with a single polynomial, one point with a single commitment. So now, you know, for each of these evaluations, we're going to have that quotient that represents those evaluations. So we'll have like QA for this evaluation. QA. Let's just say QA of X here. We'll have, I should use numbers. I want to represent it with different values. Let's just say, let's use numbers in this case. So we have a quotient that represents this. A quotient that also represents, let's say Q1, Q2 of X. Another quotient polynomial that represents the evaluation of this. Another one that represents this. Another one. So we have all these quotients that represent these evaluations. So now, if we add all these quotients together, it will give us another polynomial. Yeah, it should obviously give us another polynomial since they are all polynomials. And when you add polynomials, you get another polynomial. Yeah. But I know that the degree of the polynomial should still be within the highest degree of those quotients. Yeah. So if we now have a new polynomial, we call it like g of x, that is the sum of all these quotients. Q1 x plus Q2 x. So we have this polynomial that is the sum of all these quotients. So now if we commit, you know that the verifier on the other chain, like the verifier that is trying to verify these proofs, it only knows the root commitment. So in the end, you need to prove to the verifier that everything you are doing like can be found inside this root commitment. So now we have this. So now to ensure that someone does not like manipulate the polynomial or something, we want to like the essence of this proof is to show that when you add all these quotients, it gives you another polynomial. So that's the proof that the sum of all these quotients is another polynomial. Because like we can only commit KZG we can only commit to actual polynomial. We can't commit to algebraic fractions. So we need to ensure that the essence of the proof is just to prove that this is a polynomial, and because of the composition of this new polynomial we have, we can implicitly know that if this is a polynomial, then he must have committed to the actual quotients for the evaluations of all these other polynomials. Because we will split, like, the verifier is going to split it into like two portions that will allow the verifier to know if there is any like misrepresentation in any of the evaluations.
In this G polynomial,
Yeah.
what are we training as X? Is it going to be like the summation of all the proofs also?
No. We'll use a random value to evaluate it. This new polynomial, we use a random value to evaluate it. But before we even add them together, we can actually multiply them by a random value to ensure that, like in some weird cases, when you add polynomials, some terms are going to cancel out. Even if they are fractions, some fractions can just cancel out each other. Yeah.
Half plus half is 1.
Yeah, or like minus half plus half.
Okay, 0.
Yeah, others can, yeah. So some fractions can cancel out. And it will now be as if, even though most of these quotients are not polynomials, it can still appear that they are polynomials. So now we want to multiply it by a random value, multiply each term by a random value to ensure that, nobody is manipulating the actual polynomials by using a scheme that will make it cancel out when they are not actually polynomials. Like when each of the quotients are not actually the evaluations of anything. So we'll first generate a random value. So let's say R is our random value. So now, to ensure that this R also cannot be is binding to the prover, we'll use all the inputs as the value for R. Like we'll hash all the inputs that the prover is going to provide to the verifier. So that means we'll hash all these evaluations. Yeah, basically. We'll hash all the evaluations and all the commitments.
That's yeah.
Yeah. So we'll hash all the commitments and all the evaluations. Yeah. To generate this random value. That means we'll hash HA HD to generate a random value. Yeah. So now we now multiply the random value by each term in increasing powers. Like we now say R0, R1, R2, R, yes, 7, yes, something like that. So by multiplying it by this random value that we know that the prover cannot gain, we can be sure that, okay, if this g of x evaluates as a correct polynomial, we can be sure that each of the individual quotients, they were also polynomials and not fractions.
If you are to, like, for the random values, if you are to increase each of the power by 1,
Yeah.
like that means you cannot mix up the arrangement of each of the commitments.
Well, you can do, you can add them anyhow. It doesn't really matter.
You don't get it?
Yeah.
If you are to multiply
No, you know, like,
first one with the second one and mix it up and make that one R1 and it should be different.
yeah, as long as you multiply, like, as long as you, yeah, the verifier will know the ways, like, you want to add them, basically. You have to, it has to know how.
Must ascertain which way it wants to do it.
Yeah, based on how you implement it, you know the order in which you want to be adding the polynomials, the quotients. Yeah. Because they will basically give you, he will give you, like, the prover will provide the inputs that he used in order. Then you also, like, just follow the same order they provided for everything. So now when we have this now, the prover can commit to this new polynomial. So let me, okay, so now let's write this in. Let's write it in like a notation that will make it easy to work through. So we have a group of polynomials. Let's say I of I 0, 1, 2, let's say k minus 1. Or n minus 1 rather. Let's say we have these polynomials, this list of polynomials. Like I want to use a notation that will make it easy to work through. So we have this list of polynomials and we have evaluations for each of these polynomials at, let's say we have, these are the inputs to the polynomials. We have z of 0, z of 1, 2. So we have these inputs. Then we have the evaluations, y of 0. So we have these evaluations. So now, for each of these, we know that we'll have like a quotient to represent it, Q0, Q1. We know we'll have like quotients to represent each of these evaluations. So now we now have G of X, which is the summation of all these quotients from 0 multiplied by the random value, raised power 0 raised power n minus 1. Yeah. So now we can say G of X is just equal to like R of I Q of I rather. So now this, but we defined what a quotient was previously in like the KZG scheme. So a quotient would be this R of I. So we know that this Q is defined as phi I of x minus y of I. So we know that the quotient is defined by this particular polynomial. So basically, this is what g of x is equal to the summation of these polynomials. Then we can now have the commitment to g of x. The person proving is going to generate a commitment for this polynomial as, let's say, that is e. Let's say g of, remember our secret key equals to e. So that's the commitment to this particular g of x. So now, from here, we can actually split this g of x into two. We can say is equals to two summations now. Of yeah. We know g of x can be split into these two. Yeah, where's Ri? Yeah. We can split g of x into these two. So now, you know, like this left-hand side, or this second equation, it has all the things that the verifier knows, that the prover is going to provide to the verifier, like the evaluations and the inputs. So the verifier can calculate this part of the equation by itself completely. Then this one also, if the verifier can also calculate this part by itself, if you provide, like, if you express it in like a commitment form now, the prover will provide the commitments to each of those polynomials, each of these individual polynomials. Then the verifier can also compute this side of the equation too. So let's say we now have, let's say g1 minus g2 of x. So we now have these two parts that so let's say this are now our equation. Now we want to like have a random value at which we want to evaluate this polynomial. We want to choose a random value that we'll use to evaluate this polynomial. So we can choose another random value. So this random value can now be to ensure that we are immune to any form of malicious polynomials or malicious proofs. We can make this random value that we are evaluating this polynomial be the hash of the commitment to this polynomial and one other value. Let me see. Yeah, okay. We can make it the hash of this commitment and the hash of this other random value. So we can say this random value can be the hash of R and E. We concatenate the two. So we hash these two to get another random value that we want to use to evaluate this polynomial to see if it's actually a polynomial. So now, because the verifier knows this part, and basically, we can write this G1 like the commitment to this. Remember, KZG is homomorphic. It's additively homomorphic, so you can add commitments. So if we want to get the commitment to this section, we can just add all the commitments to all these polynomials. So we can say, like, let's say the commitment B to G1 of this, it will be it will be Ri. So it will be this commitment here. So where Ci will be, let's say, the commitment to all these individual polynomials that the prover is going to provide us with. So now, from here, the verifier can also calculate this value. So basically, the prover is giving us, number one, the prover will first give us this commitment, the commitment to this g of x. Then the verifier will do the rest, and it also provides a proof of evaluation of this at this random value. So now, this b, let's use this other part. Okay, no, let's just use it. Okay. So now we want to. The next step is to to generate the proof, get a proof for the random evaluation of this polynomial. So now we can rearrange this function, this thing, to form a new polynomial kind of. So we can have g2 of x equals to g1 of x minus g of x, basically. This rearrangement will also make this, it will be like a polynomial in some way, this arrangement. So now we can, based on the verifier knowing, evaluating this g2 of x, let's g2 of x at this random value be y. So that means g2 of, so let's say the evaluation of this part using this random value. Let's say we use this random value to evaluate this portion. We have this, we get this y. So now we can see that y equals to this. But from that, how we derive the quotients for the evaluation of a polynomial, this already looks similar to that kind of scenario now. Since we know that this side, this portion, they are also polynomials. And we know the commitment to this, the commitment to this. The commitment to this g1 of x is what? This b. This g of x, that's the e that was provided by the prover. So we can say y equals to what? Let's say, is it b? No. B minus e. So this, we need a proof for this statement. A proof for this opening commitment here. That the evaluation of this y is correct. We need a proof to show that this is actually correct.
Is y a commitment or a y?
No, y is a value.
So did it prove that? But those two are commitments, right?
Yeah, but we are working in elliptic curve elements, so everything is going to be a group element too. So this, if we look at this portion as a polynomial and we say that the evaluation at this random value, evaluation of this particular polynomial, this g2 is y. So we know the usual KZG proof will be, okay. The usual KZG proof will now be what? The polynomial. Then minus the evaluation. So that will be y at the, is it point of evaluation? What's that? Minus this random value. So if it's just they just rearrange the equation to make this like the subject and make this a polynomial. Then, since the verifier knows this, it already knows this. So if you provide a proof for this statement, the verifier can fill in the gaps and use the pairing check to know that, okay, these other commitments you provided are correct. But I know like the verifier doesn't know this commitment. It's the prover that will provide it. So in the actual proof, we need to use the commitment. So it will now be this minus y. So this will be the actual proof. This part is provided by, this is the only thing that in this proof that is provided by the, yeah. So the prover will actually provide this proof. But like to now verify this proof, we'll use the pairing check. Equals to yeah. Now we'll check if these two pairings match before we can say, okay, this proof is what do you mean? It's supposed to be pi. Yeah, this is pi. We'll check these two if they match, because the verifier provided, the prover provided this commitment to this G. Then the verifier computed this B. It's also computed this Y. So when the prover provides a proof for that evaluation at this random value, the verifier also knows what the random value is, because it will calculate it using that hash. It will also do this hash. So the verifier also knows what this other random value is, because it's the hash of all the initial inputs to the, yeah. So it will hash that to give us this. So now we have this pairing check to verify that, okay, this proof is correct. So now you can see that the proof, it has become just one, like we have reduced the proof from multiple group elements to just one group element. So imagine we wanted to prove like, if we wanted to prove 1,000 things, we'll still end up with one group element. The only difference is the number of commitments, intermediate commitments we'll need to provide. So let's say in this case now, if we wanted to prove this, the only thing we need to provide will be these commitments. Yeah, we need to provide these commitments, and yeah, and that's all. The verifier already knows this CR. So provide this, and obviously we'll provide the leaves. We'll provide the hashes of the leaves. We'll also provide this, since we want to prove this too, provide this. So it has reduced the size of our proof from multiple proof elements into just one proof element by just checking that this thing is actually a polynomial. This g of x is actually a polynomial, not a fraction. Yeah. So that's basically how it works. So now, the other portion is, most of these things, if like, like evaluating polynomials is kind of expensive. Like if you are using the coefficients of the polynomial to evaluate it in coefficient form, basically. So we can like optimize it by reducing, instead of using the coefficient form to do all these evaluations, we can now use like the evaluation form. So in the evaluation form, we have, we just have basically like a vector. Yeah. We have a vector that says these are the inputs to n minus 1 or k minus 1, and these are the outputs. Z.
So you don't actually have a polynomial.
Yeah, we're not representing the polynomial by the usual coefficient form. So if we have this, like you can evaluate it's easier to multiply polynomials and divide them in this form. And like, let me describe. So, this thing is so you know, to compute this. I'm coming. Say we have, like, let's say we want to compute the commitment to a polynomial in its evaluation form. You know, like we can interpolate, we have this Lagrange Lagrange basis, basically. So you have a polynomial, like what's the Lagrange is, forgetting the definition for that Lagrange function. Yeah. So this is one of the optimizations we can do first. We have the Lagrange polynomials that we discussed in the last section. Remember, like you have different Lagrange coefficients, basically. So we have, to get the full polynomial, you get all the individual Lagrange evaluations for that polynomial, then you now have the final form of the polynomial. So the polynomial will now be f of x. It will be adding all the Lagrange bases. Yeah. Yeah. So the polynomial will be the addition of all these Lagrange bases. So we can also compute the commitment in this form. So now if we have, let's say we have the commitment now. What's L of? We have okay. So this will prevent us from like converting our evaluation form into a coefficient form. You know, like if we wanted to compute we have these inputs, we have these values. To now compute the commitment for this polynomial that represent this, we have to first interpolate, get the polynomial, then commit to that polynomial in its coefficient form. But with the Lagrange basis, we can just get the Lagrange basis for the polynomial, sum them together, then commit to that, to the Lagrange polynomial, the final Lagrange polynomial, without having the overhead of first interpolating these. I know that because we're using the roots of unity, we can pre-compute all those LIs. Since we know the size of our polynomial, we know the omega values, and we can pre-compute them and use them to just speed up the computation of commitments. So that's one way to optimize the proving system.
Looking at this, it seems like we can do this for FFT
Yeah.
also.
You can also use this to convert. You can use because we are using roots of unity also, we can also convert between the coefficient form and evaluation form using FFTs. Like if we take the discrete Fourier transform of the evaluation form, yeah, we'll get of the coefficient form, we'll get the evaluation form. So if we take the inverse, we'll get if we take the inverse of the evaluation form, we'll get the coefficient form. Yeah.
Well, when we are representing this in an algorithm, we can assume that this is just a vector array.
Yeah, just a vector of the inputs to map to, it'll be a vector of like maybe omega comma z. Yeah. So that's the Lagrange, using the Lagrange polynomial is a way to speed up the computation of commitments without doing the conversion back to coefficient form, then computing polynomial. I think we can also multiply and divide in the coefficient form too, in the evaluation form. Yeah.
Is there a way, like a standard way I can assume this representation is named?
It's named. This representation.
Yeah.
They just call it evaluation form. Yeah. There are also some complex parts. Yeah, I've not looked deep into it, but where you divide, when you meet a point, like for the evaluation form, if you get to a point where you need to divide by 0, you cannot really do it directly. So you have to use some extra. Yeah, I've not looked in deep into it, but you can divide directly by 0 in evaluation form. So you have to, like if, let's say you want to divide two polynomials in their evaluation, like let's say we have f of x and g of x. If you want to divide these two, you can divide them in coefficient form and evaluate the result at a point. But if you have the evaluation form, you can just divide the evaluation form. But let's now say that this is 0 in some way. And yeah, and you want to do f of x over g of x. You can, let's say the value is f and this is g. You can't really divide by 0. So you have to use some other method to achieve that. Yeah. I think that's the part where the evaluation form doesn't really work. When you meet division by 0, yeah, you have to use something else.
You cannot really predict if you meet division by 0.
Yeah, that's why you have to implement the check by default. Yeah, I think there's an implementation for dividing by 0 in evaluation form, but it's kind of more complex. Yeah. And also, if we're using the roots of unity, we're using the roots of unity to represent to interpolate our polynomials in this scheme. But now, when we get to this point, where we want to evaluate, where's that? We want to evaluate at these random values that are not part of the roots of unity. Like this, where's that point? And those polynomials, since everything will be in evaluation form in the first place, like everything we're doing here, we'll be using evaluation form when we want to implement it. But we now get to a point where we want to evaluate these, like let's say this one, this y now. We want to do it in evaluation form. But this random value that we're using to evaluate it is not part of the root of unity. So we'll need to use, I think, the barycentric formula to evaluate it. Yeah. Like, remember this g2 of x? We said the verifier has to evaluate what g2 of x is. And it's kind of like a polynomial. So now, you cannot evaluate, because our polynomials were interpolated, they are in evaluation form. We're representing everything in evaluation form. You cannot, in the evaluation form, you cannot evaluate values outside the domain easily. So you need to use another algorithm to do that, to evaluate.
You give him this W set and this Z set.
Yeah, you can, yeah. This one, the evaluation form just represents, it's just the mapping of inputs to outputs. But now, outside this, since you don't have the actual polynomial, you didn't interpolate to get the actual polynomial. In this form, you cannot pick out, like there's no way to get a value for something that is not in this map. Yes, so you need to use the barycentric formula.
And this times for the barycentric.
Let me see. I think. Yeah. But I think this, like we said, if we have the evaluation form, I think the barycentric formula is f of z equals to, if we're using the roots of unity as our domain, d minus 1 over d So like this is how we evaluate it. You know, this f of I is like the evaluation. Yeah, evaluation form. Like the evaluation of that polynomial at I. So let's say this is the random, this is a value outside the domain. We want to evaluate f of x in its evaluation form. Yeah, at z now. But since we have the evaluation form of this f of x and our domain is the root of unity, there is no way to pick out something outside this domain from this map. So this is the formula for getting what the evaluation of this is from the evaluation form. Yeah. So I think because we are doing an evaluation form, it will reduce the computation complexity for coefficients, like evaluating coefficient forms.
What is z to the power of 5 in this case?
D.
This z,
This is the
z.
z. Like this is the value we want to evaluate now.
Yeah, the power of what?
Oh, it's not, it's D. Yeah. D will be the degree of the polynomial. I think that should be it for now. Or does anybody have something else? Does anybody have anything to add? Yeah.
But I guess you're not wrong with it.
We can round off now. Yeah. Okay. Yeah, we're working on implementation for our ISMP. Yeah.
I can imagine your test
Yeah.
sheet.
Open source.
Yeah, it will be open source when it's done.
When it's done.
Yeah.
How is your test sheet for all these scenarios?
And in implementation, you have to do everything. I think you have to modularize the different parts. Yeah. Okay. Yeah, you have to do all this. Yeah.
And KZG too.
Yeah, KZG.
Could be a meeting.
I think the trees actually, like these parts are kind of implementing the actual, these polynomial evaluations. They are kind of the easier part. I think incorporating them inside the trees where you need to do a lot of work. You know, on their own, they'll just be like basic functions. You get polynomial, compute this, compute this, compute that. So, yeah. Yeah, that's nice. It's nice. Yeah. So thanks for coming to this session.
Stick around for the pizza, by the way, as well. Thank you for leading the session, David.
Yeah, it's a pleasure.
Some new mark to start the year.
Mine is not like a question, maybe like a suggestion.
Okay.
If you can have this more, so like the space in between the one and the two, the one and the two.
Right.
Mm.
Okay.
Yeah. And I know like maybe 6 for that might be a bit. Yeah.
I think it's doable. Actually, we are starting a co-working session, so people will to come around more frequently. Actually.
Oh, a co-working session space.
Yeah, people can come and co-work here with us. Yeah.
Funny thing, I was thinking about that, like I was like, that's interesting.
Yep. Yeah, we can end the session, I think.
Yeah, I can stop the stream. Yeah, you can. Cheers.